Without like,
Well, it can't recognize that. That'd be crazy. No person can do that either. That's just to say. But you see, it says Clemson Tigers, and then it pulls out to the real estate. But it knows it's taken care of. Respect to it. Yeah. I try to get it. That's like the other use of that. It's not like that way. It's crazy. It's not perfect. Right, it's not like a miracle or this thing. Yeah, it basically can do stuff with you. Yeah, you just have to do, but yeah, like it tells you every day, like what you're reading, you just check the box next. I mean, I bet it was literally. So there's no good morning, everybody. Thank you for being here the Friday before break. We got a lot to get through, so let's go ahead and get started. Today, we're talking about coordinate systems, vector spaces. I'm going to give a little motivating example to start for what's to come. So let's start in R3, where we are comfortable with what things look like. And we want to look at just any generic element that I'll call A, B, C in R3, our vector space. So we think about A, B, and C as the coordinates of that vector in the x direction, in the y direction, and the z direction. And we can represent any of the infinitely many points in this vector space by just the three coordinates in those three directions. They're completely determined by this. If we write this in our normal vector notation, we can always break this up into A times E1 plus B 0, 1, 0 plus C 0, 0, 1. Where these three form a basis of R3. This is the what we call the standard basis in R3. I bet Jim's probably used that terminology before, right? So if I give you any elements in R3, I can just think about it with respect to its essentially scale in this direction, scale in this direction, scale in this direction, or its weight in each of these three directions, completely determined by how far it goes in the 1, 0, 0 direction, the 0, 1, 0, and the 0, 0, 1. So that's really nice. And our goal today is essentially to be able to do this for any vector space. So if I give you a really abstract vector space, I want to be able to write it in terms of simple coordinates in Rn, and that's going to make our analysis of the vector space much easier. So let's not forget today. But that leads us to our first theorem. It's I believe 7 in your book. This is the unique representation theorem. And so what this theorem says is that if we let B, and this is going to be the same notation for pretty much all of them today, you want to be a basis for a vector space B. And we take any x, so or any x in B, there's a unique set of scalars I'm going to call these C1 through Cn, such that we can write x as a linear combination of these vectors with these scalars. So x is equal to C1 U1. So what is this telling us? It's saying if you give me a basis for a vector space, then any element in X can be written uniquely as a linear combination of the basis, right? So let's prove this really quickly because the technique that's used is kind of a common one for proofs in linear. So first, we want existence, and I don't even really need to do anything to prove that a linear combination like this exists, because we assume that B was a basis, and so for any x, it's going to be in the span of this set. So we're going to get some linear combination that's equal to x for any x, but we need to show that this is unique. That's going to be very important for today. So these are the only scalars such that there's a linear combination of these vectors that's equal to x. So let's assume that there are two. I'm going to call one. So let's assume that A1, B1 through A and Bn is equal to x. So this one linear combination is equal to this same linear combination. So our goal is now to show that all the AIs have to be equal to the CIs. Then we've shown that uniqueness. Any ideas of how we would do that? We're gonna want to use, we already used the fact that a basis spans, but the other property of a basis is that it's linearly independent. And linear independence and uniqueness often go hand in hand. So what I'm going to do is subtract over everything from the right side to the left side, and I'm going to combine these scalars. So what I get is A1 minus C1 all the way up to AN minus CN equal to 0. So I subtracted everything from over there. And now I get another linear combination of our basis, but now it's equal to 0. And by the linear independence of our BIs, all of these scalars have to be 0, because that's what it means to be linearly independent. The only linear combination that gives us 0. So all of these scalars, A1 minus C1 equal to AN minus CN is equal to 0. And that's enough to give us that A1 equals C1, A2 equals C2, and so on. Right. So we've shown that because of the spanning property of this, we can write anything as a linear combination. And now we've shown that these scalars, or we call them the weights in each of these directions, are unique. And that's going to be really important to what we want to do today. Okay? Fine. Definition. Same kind of setup. We're going to suppose B is a basis for B. Which is just any vector space. And X is any scalar into B. Then we say the coordinates of X relative to B or we can also say the beta coordinates of X. I'll probably use this phrase most. Are the unique scalars, or weights we could call them, such that we're able to write it as a linear combination of our basis vectors. So now that we know that they're unique, if we fix a basis for any x, we're going to call its beta coordinates these scalars, these weights. And notice how this is similar to our example here, right? This is our basis, and this a, b, and c would have been our weights for any given vector. Now we're saying fix any basis. We want to be able to refer to the element x only with respect to these scalars, these coordinates. So this is kind of the central idea for today. All right. Continuing kind of with this definition. If these C1 through Cn's are the beta coordinates of x, then introducing a new notation. So this we refer to as the coordinate vector of x. With respect to beta. Or we call the beta coordinate vector. So given any x in my vector space, this n tuple, this element of Rn, is its beta coordinates is the scalar such that I can write x as a linear combination of my fixed bases. So what is nice about this? Well, now for any arbitrary x in an arbitrary real vector space, I have a way of having this correspondence between that element and an element of Rn where things behave a lot more nicely. And then finally, the mapping x to its beta coordinates. By mapping, I just mean it takes any x to beta coordinate vector. It's called a coordinate map. Which is going to be very important. It's very soon. Questions about these definitions? Okay, let's look at an example. Look at R2 first. So consider the basis. So this is going to be R1. If we wanted to verify that this was the basis for ourselves, we could do so pretty quickly. They clearly have to be linearly independent because of the 0 here. If these add up to 0, then the scalar on this must be 0, but then this times the scalar is 0, so the scalar must also be 0. And then we get spanning pretty quickly as well, because you can subtract this vector from this vector and divide by 2, and then we'll have 1, 0, 0, 1. And it turns out that any linearly independent set in R2 is actually a basis. So that's all we need. That's kind of a spoiler for 4.5. So that's our basis. And this is n R squared. And Suppose we don't know what x is, but we're given its beta coordinates to be -2, 3. We want to find x. So this is kind of the easier direction. If you're given the coordinates, all you have to do is basically form the linear combination and you're going to recover what x is. The way we do that is we simply say x is going to be -2, 1 plus 3, 2, because this is my v1 coordinate, this is my v2 coordinate. This is going to give us 1, 6. Pretty simple, right? Going in that direction isn't hard, but we'd like to be able to go in the other direction, right? Because our kind of goal here is we're given a vector space that's complicated. I want to be able to write a vector in terms of coordinates, so I can think of it as a vector in Rn in some sense. But before we do that, let's so we're looking at this same x again. The entries of 1, 6 are just the coordinates with respect to the standard basis. You guys know what I mean when I say standard basis for Rn, right? It's just beta is u1 2, which is 1, 0. And we kind of get why this is the standard basis, because it's the kind of what we always deal with, right? This A, B, C in R3 in general, those are just the coordinates with respect to the standard basis in R3. And we're going to see in a minute why exactly this really is the standard basis for Rn, because it's going to give us a very nice property for something that's coming up. Okay. So if we're given the coordinates of a vector, we see it's not very difficult to recover the vector. But like I said, we want to be able to go the other direction, right? Let's assume that we're given a basis u1, u2. And we're going to let v1 be 2, 1. V2 be -1, 1. And then we're going to let the x in our vector space be the vector 4, 5. And we want to find the coordinate vector so now we're given an element, we're given the basis. I'm asking you to find the weights. So essentially what it's asking us for is find the C1 and C2 such that this is equal to x, right? So we can pull some of this stuff in. We have this, and I want to rewrite this as the following. So now that we have it in this form, we can see it simply becomes a question of, is this matrix invertible? If so, I'll have one unique solution, which I should have, right? Our unique representation theorem, which I've already says there's only one set of scalars that works. So this should be invertible. Why do I know that this matrix will 100% be invertible without even checking the determinant? Thanks. The columns are linearly independent, right? The columns come from our basis. Basis is linearly independent, and a matrix is going to be invertible if and only if its columns are linearly independent. So I don't know if do you guys know the trick for doing the inverse of a 2x2 matrix? You divide by the determinant, you flip the A and D coordinates, make it negative. In case it's not clear where that's coming from. So I'm going to multiply by the inverse on both sides. So I just get C1, C2. The determinant of this is 2 minus 1, which is 1/3. And then I'm going to flip these two, and I'm going to flip the sign on these. And then it's just a little. Okay, so now we've found our coordinates. And the nice thing is, these are always really easy to check that you did them correctly, right? Because this tells me that 3 times this plus 2 times this should give me that. And it does. So we've done that correctly. So once again, we have identified a x with a vector in R2, which is very, very nice. So now we are going to need another definition. So the technique that we used here is kind of the general technique that we always want to use. Yeah, I'm sorry, I don't know. How do you use the 1/3? This is the determinant, 1 over the determinant. Okay. So yeah. If you don't know this trick, it's very nice. You might know this one. So if this is, we call this A, then its inverse is 1 over the determinant of A. And then you flip these and change the sign of those. So that's how I got this as the inverse. And I multiplied on both sides. Okay. But in general, you're going to need to, set up a matrix with the identity and your matrix and verb reduce and find it that way. But 2x2s are especially nice. Not as nice as 1x1s, actually. Those are my favorite to take the determinant. All right. Where were we? All right. Oh, but before I get into this definition, what I was saying is this is going to be our general format, right? If we're given a vector and we want to find how it's a linear combination of these, we can always write it as this matrix times the vector of scalars and solve just like we did. So now we're just talking about our n. Once again, let's let this be a basis of our n. Then this matrix is called the change of coordinates matrix. From beta to the standard basis in Rn. we can kind of see why that makes sense from our example over here. Because if you're given any x, and we're writing it as a linear combination of these vectors on our basis, right, which we know that we can do, then x is simply going to be this matrix times the coordinates of x with respect to beta. And that's exactly what we did here, right? Our x was the change of coordinates basis matrix times the coordinate vector. So what does this tell us? It says if we're given an x, if we're given the coordinates and we want to get back to x, the way that we do that in general is just by multiplying by this change of coordinate matrix. So what does that tell us? Well, if you remember, we call this mapping where we take the x to its coordinates, the coordinate transformation. What can we do here? Well, in general, because of what he said earlier, these are linearly independent. So our change of coordinate matrix is always going to be invertible. So this, when we have this, we can always move the inverse to the other side. And now we have a nice way of finding the coordinates of x, just given our x, which we said, right, is the harder direction. If you're given the coordinates, you just plug them in. But if you're given an x and you want to find its coordinates, well, you can multiply on the left, remember, by the change of coordinates matrix, and you'll get your coordinates back. So instead of having to solve a system of linear equations every time, all we have to do is find the inverse of this matrix one time, and then we can always shift. So that map that I referred to over there, which takes x to its coordinates, is determined by left multiplication of this with this matrix. So we wanted a way to take any given x in any abstract vector space and write it as a set of coordinates, write it as a vector in Rn, and now we have a way to do that. We want to see why that is especially nice. So if I just give you any random vector space, and I give you an x in here, and you have some basis of n elements, maybe these look horrible. Maybe these are objects that are really hard to deal with, but you know that it has a basis over R. It's a vector space over R, and it has a basis. Then this map allows us to think about that element as just something in Rn. And it turns out we're going to be able to do arithmetic just as if this actually were an element in Rn, which is what the following theorem is going to tell us. We may call this the coordinate mapping theorem, but it's theorem 8. That says that the coordinate map takes us from our x and maps us to beta coordinates of x is a one-to-one linear combination. Maps onto R. So why do we care? Right? Well, the fact that it's one-to-one and onto makes it a very, very special kind of mapping. I'm not going to do the proof of this. But there, it's on page. So what's the significance of this? First of all, it's a linear combination. It's a linear transformation. I apologize. What that means is, and we kind of get this from the fact that this works for the matrix. Given any linear combination of vectors in my space, then you're going to be behaving like this. So we've dealt with linear transformation before, but the fact that it's one-to-one and onto tells us a lot more. It actually tells us that this mapping, I'm going to refer to the coordinate map, is an isomorphism. B to R. And that is super, super, super important. What that means, if you've never seen this term, comes from the Greek words iso, meaning the same, and morph, meaning structure. This is a fundamental idea in linear algebra and in abstract algebra. You want to say that two abstract objects have the same structure. And for vector spaces, what that means is that there's an isomorphism between them. What we'd say is, if there's an isomorphism between them, V is isomorphic to Rn, or V is isomorphic to any vector space. And an isomorphism is exactly this. It's a linear transformation, which is one-to-one and onto. So for our purposes, what does that mean? It means V is algebraically, structurally, computationally exactly the same as Rn. If we can find a mapping like this between two vector spaces, they're the same thing. We're just writing the vectors in different ways, which is a really, really strong result, but a very useful result, because what that means is if I give you a vector space and doing computation in that vector space is really hard, well, we have recourse to say this is isomorphic to Rn. I can do all my computations there instead, and the analysis is going to be exactly the same. So let's look at an example of why this is so nice. Let's consider this basis the standard basis 1t squared t cubed in p. And remember, these are just polynomials of degree less than or equal to 3. So a typical element of this vector space, called P, I form, we generally would write any polynomial like this. So the nice thing is when this is our basis that we're using, we already write all polynomials in terms of their coordinates with respect to the spaces. So it's very, very easy to see that the coordinate vector of the with respect to this basis is just A0, A1, A2, A3. So this map, which takes P to its coordinate vector, is an isomorphism between P3 and R4. So what this tells us is they're essentially the same thing. They really are. Like, we're just calling these polynomials, and we're calling those vectors, vectors in Rn, but they behave the same way. Because of this property. If you add the P1 and P2 over here, and you add their images over here, you get the same thing. So if I want to figure out something about P or about P3 in general, I'm really asking a question about Rn. And this is really, really nice. So last example for the day. Yeah, let's show exactly why this is useful. But we're going to do P2 instead of P3. So P3 is isomorphic to R4. I get to guess what P2 is going to be isomorphic to? R3. Mm-hmm. And that's because of the size of our basis. Turns out any basis in P3 is going to have size 4. You're going to get it. That'll be material for the next section. And any basis in P2 is going to have size 3. And it turns out all you need to know is the size of the basis, which has to be unique, to know it's going to be isomorphic to Rn, where n is the size of that basis. So let's do a little bit of computation. We're going to let B, our basis, be the standard basis, but now in P2 instead of P3. And we're going to consider the following 3 vectors. We want to use this coordinate map. Show that the following 3 vectors, 1 plus squared, 2t squared. 1 plus 2t squared, 4 plus t plus 5t squared, and 3 plus 2t are linearly dependent. Say, I could just give you this problem without any recourse to a basis or the coordinate map. I could just say, hey, I'm giving you these 3 vectors and 3, show me that they're linearly dependent. Yeah,
This isn't P2, right?
Yes. Thank you. I'm sorry. So I could say, here are three vectors, show me they're linearly dependent. So what do we have to do? We need to show that one of them is a linear combination of the other two, or equivalently, that we have a way to add these together, a linear combination of these that's equal to 0, where not all of the scalars are 0. So how would you do that? It's a little bit more complicated than in the R3 case. In the R3 case, we know how to do this. And you certainly could do it directly, but it's going to be a lot trickier. Instead, I want to think about these in terms of their beta coordinates and solve the problem that way. So the first thing I need to do is write out the image of these. So this is going to be 1, 0, 1. 4, 1, 5. And 3, 2, 0. Yep. So now I have their images, and I know that these elements are exactly the same as these in their respective spaces. So I'm going to carry out the analysis in R3, and that's going to allow me to solve the original question. So basically, if I let the columns of a matrix A be these vectors, we're trying to solve AX is equal to 0. Right? So we can make a little augmented matrix where these are going to be my columns 1, 0, 2, 4, 1, 5, and 3, 0. Then we'll let these represent. So first, I can do R3 minus 2 times R1. Remember, we don't want to say equal, we want to do this. It's an equivalent system. This is left alone. This is left alone. And I'm going to get 0 minus 3 minus 6. And now I'm going to do R3 plus 3 times R2. I leave the top 2 rows alone. And now both of these are going to cancel to give me a row of all zeros. So this matrix has linearly dependent columns, meaning that these 3 matrices are going to be linearly dependent. And that is all that we need to do to say that those polynomials are also going to be linearly dependent. So, in fact, it'd be not too hard from here to solve the following. So this is our non-trivial linear combination of our 3 coordinate vectors that gives us the 0 vector. And this implies that 2 times this vector minus 5 times that vector, that polynomial, minus our last one. And you can verify pretty quickly that this is true. But we didn't have to do anything at all with polynomials to get this result. And that's really the crux of why we care about doing this. As soon as we found the image of these elements in Rn, we can do all of our analysis in Rn and never have to worry about polynomials again. And then once our analysis is done, by the linearity of the map, because this linear combination is 0, this linear combination has to be 0 as well. And we can just transform back. Because our mapping, we said it's 1-to-1 and onto, it's also invertible, it's a bijection. So I can go forward and I can go backwards freely between any vector space and Rn. And which Rn is going to be, that n is just determined by the size of our basis. So in this case, we had a basis of size 3, so we're isomorphic to R3. We can only have one, we get multiple bases for this, but they always have to have size 3. And we'll see why that's true in 4.5. I keep thinking you guys end at 9:50, so I kind of rushed this. I was trying to rush to get it in. But do you guys have questions about any of this material? Then I'll let you go 5 minutes early. Enjoy your break.
Yeah.